Page 2 of the quiz. L'Hopital's rule, you substitute in, you see what you get. Natural log of 1 is 0, right? Natural log function looks like that. So if you put a 1 in the top, evaluates to 0. Put a 1 in the bottom, that evaluates to 0. So since the top evaluates as 0 and the bottom evaluates as 0, we get that 0 over 0. That means we can use L'Hopital's rule. L'Hopital's rule says take the derivative of the top and the bottom and try the limit again. So that's going to be limit as x approaches 1 of, it'll be 5 over x on top, and the derivative on the bottom is 1. And let's sub a 1 back in there. You get 5 over 1, which is equal to 5. So there is your limit. Okay. Second one. It's currently not a fraction. So rewrite this, limit as x approaches infinity of 4x over e to the x. If you substitute infinity in, the top is going to approach infinity, bottom is going to approach infinity. It's that infinity over infinity setup, so we can use L'Hopital's rule. This will be the limit as x approaches infinity of 4 over e to the x if you take the derivative of the top and the bottom. Okay. Now, if you put the infinity in there, you get a huge denominator, and the numerator just stays 4. 4 divided by a really big number is going to approach a limit of 0. Okay? All right. 1950, the population of Cincinnati was a little bit over 503,000. By 2000, it had dropped to 331,000-ish. We want a function representing the population of Cincinnati T years since 1950. We're assuming the population has decreased at an exponential rate. So they're basically telling us to use the PERT formula. I'm going to use the calculus version of this, C naught e to the k. I'll use a t there to represent time. So I would probably let 1950 be t equals 0. And we can do years since 1950. And that'll allow us to use that 503,000 as the initial value. So that would be y equals 503,998 e to the kt. Now, by 2000, that's 50 years later. So I could substitute a 50 in for t, and the population has dropped to 331,258. So we could go ahead and substitute everything into the equation like that and try to solve. Remember, you want to get the e by itself, so you want to get rid of this value here. So we would have 331,258, divide both sides by 503,998, and that's going to be e equal to e to the 50k. We're trying to get that decay constant there. So anyway, I'll divide this out. I'm going to have to do a little calculator work here. I really hope I am typing all of this in correctly. Okay, this decimal here is about 0.65726. I'm actually keeping more of it in my calculator over here. That's equal to e to the 50k. Remember, you can do a natural log here. It's a log base e of 0.65726 equals 50k. So ln of 0.65726. And again, I'm actually keeping that whole thing in the calculator, is equal to 50k. And I'll be dividing the natural log by 50 and getting k. So, all right, so I'm going to take the natural log of that previous answer, and then I'm going to divide that by 50. And this is a decay function, so yeah, our k value here is going to be a very small decimal, 0.0083935. So anyway, I'm going to go a lot of decimal places there. Go as many as you can. Actually, again, if you can keep it in the calculator, that's even better. All right, so our final function here, I kind of ran out of room, but it would be y equals 503,998 e to the negative 0.0083935 t power. Okay, there's our function. We wanted the instantaneous rate of the population in 1980. That's going to be the derivative. Okay, that's just an e function. It's got some weird decimals there, but anyway, we're still going to have that 500,000. We're still going to have the e to this decimal. We just have to multiply by the derivative of the inside function, which is going to be that decimal. So it's going to be this decimal getting multiplied by 503,000. So I'll take that decimal and I'll multiply by 503,998. And so out in front, we're going to have negative 4230.304913 e to the negative 0.00839335 power. And we want the instantaneous rate of change in 1980. 1980 is 30 years after 1950, so we'll fill in a 30 there, and we'll work all this out. Okay, so I have that negative 4,230 value times e to the, my exponent's going to be that negative decimal there, and I'm multiplying that times 30. And so the rate of change will be negative 3288.624 if I round to 2 decimal places. And let's see, the units here, it's population, and the rate of change, I guess it would be people per year. So basically it's saying by 1980, the city was losing 3,200, almost 3,289 people per year was the rate of decrease. Okay, and number 18, let's take a look at this one. All right, this is the graph of f, okay? They're explaining a function g based off this function. So g is 5 plus this integral of function f, okay? So for part A, g of 6, you'd be taking the integral from 6 to 6. The integral doesn't move any, so that integral from 6 to 6 over here starts at 6 and ends at 6. The integral will be 0. So 5 plus 0 is just going to be 5. So g of 6 is going to equal 5. Okay. For part 2, g prime of 6. Well, g prime, we're taking the derivative of this thing. So the derivative of 5 is a constant. That's going to be 0. That's the derivative of an integral. So g prime, we're taking the derivative of the integral. That's just going to knock out this integral, and it's going to give us this in terms of x. That's going to be just f of x. So g prime is f of x. In this particular case, I want g prime of 6. That means I'm finding f of 6 on the graph over here, which we can see is 3. Okay? And then g double prime, that would be the derivative of f, which is f prime, which means we're looking at the slope of f in a particular place. So if I'm looking for g double prime of 6, we're looking for the slope at 6, and it says there's a horizontal tangent there, so that means that the slope there is 0. So f prime, which is the same thing as g double prime, is going to be 0. Okay? Part B, on what intervals is g decreasing? Well, increase or decrease, that would be the derivative. So we're looking at g prime, which is f, and g prime is, of course, function g is decreasing when g prime is negative, so when this is less than 0. So on our f graph, we're looking for when f is less than 0. F is less than 0 from negative 3 to 0. F is less than 0 between 12 and 15. So we're going to say basically between negative 3 and 0, and between 12 and 15. And that's all that's going on there. The justification would be basically that function g is decreasing when g prime equals f is less than 0. You should probably say that in a sentence, but I'm not going to write that up for purposes of the video. Okay, part 3, on what intervals is the graph of g concave down? Well, that would be g double prime. We want g double prime to be, concave down means this needs to be less than 0. G double prime is the same thing as f prime, and I labeled that earlier. F prime, of course, is the slope. So we want anywhere where the slope of f is less than 0. In other words, a negative slope. So we have a positive slope of f all the way to here. Everywhere from 6 on, from 6 to 15, we have a negative slope of f prime, which of course means f prime is less than 0. F prime is the same thing as g double prime. So we have a negative second derivative in those in that interval which means the function is concave down.